This is Elasticity, or High Deborah Number Measurements, Part 3 for Polymer Rheology and Processing. In this part, we're going to talk about elastomers. And elastomers are usually thermosets with long polymer chains that cross-link during curing. And in the case of elastomers, when we're talking about cross-linking, they use the term vulcanization or vulcanizing. In most elastomers, these crosslinks are covalent, and covalent crosslinks assure that the elastomer will return to its original configuration once stress has been removed. Without the crosslinks, the applied stress would result in a permanent deformation. The IUPAC definition of crosslinking is a small region in which a macromolecule from at least 4 chains emanate and are formed by reactions involving sites or groups on existing macromolecules or by interaction between existing macromolecules. In polymer chemistry, to kind of break this down, a crosslink is a bond that links one polymer chain to another, very simply. And a crosslink polymer is something that has undergone the bulk of crosslinking. The bulk of that material has been crosslinked. This is the main distinguishing element of a thermosetting type material. Mechanical properties depend very strongly on crosslink density, and the level of crosslink density gives you different properties. Low crosslink density decreases the viscosity of polymer melts. Intermediate crosslink densities transforms a gummy polymer into a material that has more elastomeric properties, and very high crosslink densities can cause materials to become very rigid or glassy, like phenolic resins. Here are some of the basics of crosslinking. A linear polymer is a long continuous chain, mostly of carbon-carbon bonds, although there are inorganic polymers, with the remaining 2 valence bonds attached to hydrogen or relatively small hydrocarbon moiety. And here you see a AFM image of a real linear polymer. The chain length for this polymer is about 204 nanometers, and the thickness is 0.4 nanometers. So we're looking very, very small. And to kind of put this in context here, this is a 25 nanometer scale bar. They're quite long, but very, very skinny, and as you can see here, very linear. A network polymer, by contrast, is formed as a result of covalent chemical interaction between linear polymer chains or the buildup of monomeric reactions of 3-dimensional fishnet configurations. So you can see my extremely good PowerPoint artwork here. These are linear chains in space, and when polymers become cross-linked, this becomes this, where you have crosslinks between these polymers making one giant polymer chain from several linear ones. Functionality is related to crosslinking and very important. Molecular functionality is the number of reactive groups per molecule, or mole of reactant, and this dictates the potential for crosslinking. A total average functionality between reactant elements has to be greater than 2 for there to be a potential for crosslinking. In an addition polymerization, this is a vinyl monomer that would normally produce a linear polymer, but some other unsaturation is either generated or remains after that addition has occurred. And I'll show you a schematic of what I mean in the next slide. By contrast, condensation is usually a bifunctional monomer, typically AABB type, with a polyfunctional reactant. And I'll show you in the next slide what I mean by that. But this polyfunctional reactant will then form a thermosetting structure with the bifunctional monomers. So here is the schematic representation. Here you have 2 double bonds in an addition polymerization. After this undergoes Ziegler-Natter polymerization, you break one of the bonds here, but this bond reforms in the middle. And in this case, you can use a reactive diluent like styrene to free radical polymerize between chains that look like this, creating cross-linking. I believe that makes styrene butadiene rubber. And in this case, you have a very generic bifunctional reactant with a trifunctional reactant, and this can react to form this sort of network structure. Of course, A only reacts with B, so A reacts with B. There's another B moiety here which can react with A, and you can create these networks of polymer chains in a condensation type polymerization. There are a variety of factors that influence cross-linking, time and temperature not being the least of them. These are chemical reactions, and so they are governed by Arrhenius behavior, and strongly influences cross-linking. Mass. These are exothermic reactions, and the mass effect also influences the rate of reaction. Concentration is very important. The stoichiometric balances of the monomers that are present dictate the degree of cross-linking. Also, you have to have free volume accessibility of each of the reactants to each other so they can physically react. Elastomers themselves are generally cross-linked, and they're amorphous polymers that exist above their glass transition temperature, so that considerable segmental motion is possible. The elasticity is derived from the ability of the long chains to reconfigure themselves to distribute the applied stress. As a result of this flexibility, elastomers can reversibly extend from 5 to 700%, depending on the particular type of material that you're working with. Here's a cartoon. A is an unstressed elastomeric polymer, whereas B is the same polymer once it has been stressed. Once the stress is removed, it will return to configuration A if it is a true elastomer. And the dots here represent crosslinks. The molecular structure of elastomers can kind of be imagined as like a spaghetti and meatball structure, where the meatballs are the crosslinks. Application areas for different types of rubber or other elastomers are very diverse. Seals, molded flexible parts, of course tires, shoe soles, dampening and insulating elements are just a few of them. There are a variety of cross-linkable unsaturated rubbers, not the least of which is natural polyisoprene or natural rubber that is obtained from rubber trees. And this includes cis 1,4-polyisoprene or trans 1,4-polyisoprene, known as gutta percha. There's synthetic polyisoprene, polybutadiene, polychloroprene, which is known as neoprene commercially, butyl rubber, which is a copolymer of isobutylene and isoprene, styrene butadiene rubber, copolymer of styrene and butadiene, nitrile rubber, a copolymer of butadiene and acrylonitrile, ethylene propylene diene rubber. This is a terpolymer of ethylene, propylene, and a diene component, and then silicone rubber. You can think of a cross-linked elastomer as a network formed in elastomer of interconnected springs. These are amorphous, so there is no crystallinity present, and deformation of this type of structure results in constrained polymer coils, and these are also known as entropic springs. The elastic modulus increases with an increase in temperature, and this is a direct contrast with what we see for other solids. Solvent swelling reduces the elastic modulus by reducing the number of springs per volume. In elastomers, the crosslinks that you see are considered covalent. There's also the phenomenon of physical crosslinking. And the phenomenon of physical crosslinking is illustrated here, where you have physical crosslinks created by either topological entanglement or cohesional entanglement. These are often very small crystalline regions, and this is usually due to chain entanglement. Crosslinks present in elastomers are covalent in nature, and they are not altered by solvent swelling, whereas chain entanglements in a non-crosslink polymer melt can act as physical crosslinks and produce some of the same phenomenon at lower shear rates. At low shear rates, polymers are in constant motion if they're above their TG, and they can wriggle through their kind of mutual structure. This allows them to maintain a conformation that corresponds to a low energy state, and this motion is known as reptation, like a reptile, like a snake. The entanglements will not hold in a physically cross-linked system because reptation will allow for stress relaxation. Polymer chains can then diffuse rapidly enough to maintain their preferred coil-like conformation in this situation. At more moderate deformation frequencies, the diffusive motion of the polymer is a little too slow to be able to free all of the entanglements. And then you start to see an actual elastic response. At high deformation frequencies, none of these entanglements will have sufficient time to relax by reptation. Therefore, all of the entanglements will act as effective crosslinks, even if they're not covalently cross-linked. The elastic modulus will reach a plateau at frequencies above this level, and this means the network modulus, or G sub n, has been reached. The experimental time scale becomes so short that the mesh appears more like a whole rigid unit, and we're basically just looking at that stage at the stiffness of carbon-carbon bonds. So here's a schematic of the dependence of the storage modulus as a function of the frequency of the applied strain for polymer melt. And what it shows is a plateau. And this plateau, which is shown here, is the network modulus, and it extends down to lower frequencies as the molecular weight increases. Relaxation time is proportional to the cube of molecular weight. Polymer melts and high molecular weight solutions demonstrate this plateau, and they can form what's known as physical gels. And you can express the network modulus thusly, where here you have network modulus, where C is the mass per unit volume of polymer, and M sub E is the molecular weight between crosslinks or entanglements. Thus concludes the first part of Elasticity Part 3. Please stay tuned for the Part 2 video of Elasticity, or High Deborah Number Measurements, Part 2.